Hello again. This is Roger Koch Barr for the Bioelectricity course. In this segment, we're going to talk about a single spherical cell and what happens to the transmembrane voltage as one stimulates it. So the single spherical cell with a stimulus right at the very center is a situation that is, I'd say, rarely or never of interest in an experimental environment. However, it's of great interest in a theoretical context because it shows the results from stimulation in the most simple geometrical context. So let's talk about what we're talking about. Over here where I've marked I0, we're talking about delivering a current step in between two electrodes. So here's a current step. It's flat, goes up, and then it continues. The initial current is 0. After the step, the current delivered is I0. Time begins at the step. The presumption is that before the step, the membrane is at rest. That is to say, no voltage is relative to rest. Nothing is happening, and then things start happening at the time t equals 0 when the current begins to flow. Where does the current go? Well, the idea is the current goes down this wire to the center, spreads out in all directions. I've just drawn 3, but the idea is it spreads out in all directions, and it winds up over here on the membrane. So I'll put some plus charges here. And if you could imagine those plus charges going all the way around. Then, of course, there are corresponding negative charges on the other side. So I'll write some minuses over here. And the two electrodes are both spherically symmetric. The one in the center, which is just a point, and the one on the outside, which is this containing sphere. Everything here is geometrically symmetrical, so there's no spatial variation. We can ask, what now is the voltage that's produced by the stimulus? Okay, we can solve this problem mathematically. We could do it experimentally, but it would be harder than doing it mathematically. And if we do solve it mathematically, we say this is the result. The voltage is a function of time across the membrane. It's right here. Vm. Put our voltmeter right across the membrane. That voltage is equal to the stimulus current, R0. That's this voltage step, the amount of current that's being injected here. Times the membrane resistance, or the resistance of this membrane, T is the elapsed time, and then this quantity tau which is equal to the membrane resistance times the membrane capacitance. So now if we take this result as a whole, this is an interesting equation. It says what is happening in our membrane as the result of stimulation is the following thing. The voltage rises very sharply at first, then it levels off. If I give a lower stimulus, it'll go like this, a lower current during the stimulus. If I give a greater current stimulus, go up higher, but it will level off again. That's what one sees in an equation of this type. If you think about it, as time goes by, you'd say for Vm here, time there. This is an interesting situation because with, say, a lower value of the stimulus current, we will never reach a voltage up here. On the other hand, with a high value of the stimulus current, say this one, we reach that voltage pretty quickly because we have both the rate of rise and the level at which the voltage level across the membrane at which the stimulus cannot exceed. Now you might say, why does it reach this peak level? And the answer to that is understood by thinking of the membrane as a resistor and a capacitor in parallel. So if we want to think about it that way, we'd say what's happening here is our membrane is a resistor and a capacitor in parallel. We've seen this diagram before. We're putting our voltage step, our current step in over here. Once this voltage gets up high enough, our zero over here is just going to go through there. And so the charge on the capacitor will not increase anymore. That's why there's a limit. It's because the current can take this other path through the resistance. And just using Ohm's law, that current will go greater and greater as the voltage grows higher and higher. So at some voltage, it will be high enough that the whole stimulus current is going through the resistor. Well, it's a simple geometry, but still a somewhat complex result. It does have a surprising twist that we will see in the next segment. Thank you for watching.